Unraveling the turbulence, a study of fluid structure interactions. The interaction between fluid flow and structural bodies is a fundamental phenomenon encountered in many engineering applications, ranging from aerospace and civil engineering to marine and energy systems. The study of turbulence-induced vibration in fluid structure interactions is an important area in engineering and physics that examines how turbulent fluid flows cause vibration in structures. These vibrations can impact the performance, integrity, and longevity of the systems like bridges, offshore platforms, aircraft, and pipelines. Introduction. The interaction between fluid flow and structural bodies is a fundamental phenomenon encountered in many engineering applications ranging from aerospace and civil engineering to marine and energy systems. When a fluid flow past a structure, the dynamic forces exerted by the fluid can induce vibrations, especially especially when the flow becomes turbulent. These turbulent induced vibrations are, are of particular interest due to their complex nature and potential to cause structural fatigue, fatigue and noise, and even catastrophic failure. In turbulent flow regimes, is the fluctuating pressures, the fluctuating characteristics and challenges. Characteristics like unsteady and random nature, strong coupling, multi-skill dynamics, non-linearity, resonance effect. Challenges like modeling complexity, experimental difficulties, and prediction and control, fatigue and damage, etc. So what is turbulence? Turbulence is a complex, chaotic, and irregular state of fluid motion characterized by rapid variations in pressure and velocity in both time and space. Unlike smooth and orderly laminar flow, turbulent flow consists of swirling structures called eddies which interact with each other in an unpredictable manner. There are some key features of turbulence like irregularity, three-dimensional vorticity, diffusivity, energy cascade, high Reynolds number, and there are some examples which we can use in real life like smoke rising smoke rising from a fire, airflow over a airplane wing, ocean waves, blood flow in arteries under certain conditions, etc. And there are some key challenges are like complexity of turbulent flow means the turbulent flow are inherently chaotic and involve a wide range of interaction scales, making them very difficult to model or predict accurately. Second one, couple fluid structure dynamics. The interaction between fluid forces and structural response is nonlinear and bidirectional, meaning the structure affects the flow and the flow affects the structure. Third one, computational demands. Accurate simulations like LDS or DNS require massive computational computational resources due to the need to resolve small scale eddies and structural response simultaneously. Fourth one, experimental limitations. Capturing both flow and vibration data in real time with high accuracy, especially in harsh or underwater environments, is technically challenging and expensive. Uncertainty and variability. Small changes in initial conditions can lead to large differences in outcomes, making reliable prediction and repeatability a major issue. Sixth one, design and fatigue prediction. Predicting predicting long-term effects such as material fatigue or failure due to sustained turbulence induced vibrations is still an ongoing challenge, especially for critical structures like offshore platforms or aircraft wings. Im- Impact on structures. Turbulence induced vibrations can have significant and sometimes critical effect on the structural integrity, performance and safety of engineering systems. And there are some main impacts like fatigue and structural damage. It repeat it repeated the vibrations even at low amplitude can also cause material fatigue leading to cracks, deformation or eventual failure, especially in the metals and composites. The second one, resonance. If the frequency of turbulence matches the natural frequency of the structure, resonance can occur, drastically amplifying vibration amplitudes and accelerating damage. Third one, reduced lifespan. Continuous exposure to unsteady loads shorten the service life of components, particularly in aerospace, marine, and civil structures. Noise and fourth one, noise and vibrations in aeronautics often leads to unwanted noise, particularly in vehicles. Example, air, aircraft cabins and cars, which affect comfort and can indicate structural issues. Sixth one, safety risk in critical infrastructure like bridges, pipelines, or offshore platforms. Unchecked unchecked can pose serious safety hazards and lead to catastrophic failure. And there are some advantages and disadvantages of turbulence induced vibration in structures. Where turbulence induced vibration are often seen as a challenge under controlled conditions, they can also offer benefits. And there are some the advantages are like energy harvesting, enhanced mixing, flow monitoring and sensing, and structural testing. And there are also some disadvantages like material fatigue and damage, resonance risk, noise pollution, reduced performance, maintenance cost, and operation cost. The turbulence induced vibration in a sorry last conclusion. The turbulence induced vibrations in a fluid structure interactions represent a complex but critical area of study in modern engineering. These vibrations, driven by the chaotic nature of turbulent flows, can significantly impact structural performance, safety, and longevity. While they pose challenges such as fatigue, resonance, and noise, they also offer opportunities in energy harvesting and enhanced system performance under controlled conditions. Understanding the dynamic interplay between fluid forces and structural response is essential for designing resilience systems across industries, whether in aerospace, civil infrastructure, marine engineering, or energy contained research. Combined with the advances in simulation materials and monitoring technologies will be key to managing the risks and leveraging the benefits of these interactions effectively. Thank you. And turbulence in these vibrations are a key concern in fluid structure interactions, often leading to fatigue, noise, and structural damage. While challenging to predict and control, they can also be harnessed for beneficial uses like energy harvesting, understanding and managing these vibrations is essential for safe and efficient structural design. Thank you.